Okay, welcome everyone again to the final day of talks in astronomical observational techniques and instrumentation. There are 3 talks today, a special bonus, and these 3 promise to be some of the 3 best talks that we hear today in this room during this class period. Because I know that there are some talks later in this room in a different class period. The first one is Meaghan Stoelting from Rochester Institute of Technology. We'll be talking about something from Dr. Seuss, 1 fish, 2 fish, red sea fish, blue cloud.
Okay, so hello everyone, I'm Meaghan Stoelting. If you don't get my joke with my title, hopefully you will at the end of this talk. But the main motivation for this talk was I'm going to be talking about galaxy photometry, and I'm already familiar with stellar photometry, and I've done that before, so I thought I would do a step further and talk about galactic photometry today. So a brief outline of what I'm going to be talking about. First and foremost, my science question, because that's the most important thing that I have to tell you what I'm asking. And then I'm going to talk about background and the different galaxy populations and the different types of galaxies. I'll talk about my data sample. Spoiler alert, I'm using Sloan. And how I obtained that data and what I used for that. My method, I'm making a galaxy color magnitude diagram and also looking at distribution of galaxies. Next, I'll be talking about how my galaxies are distributed and answering my science question via my conclusions. So my science question is there a bimodal color separation from a random sample of galaxies? And I formatted this as a yes or no question because I wanted to dig deeper into why this would be or why this wouldn't be. And so if yes, I'm going to talk about galaxy morphology and different galaxy properties for the different types of galaxies. And if my answer is no, I'm going to be talking about my data specifically, and if I have a bias towards redshift that makes everything redder, or is using a random sample of galaxies a bad method, which I'll talk a little bit more about next. So first, I'm going to talk about something that we hopefully all know about, which is the Hubble tuning fork and how Hubble did his galaxy classification. So as you can see, on the left-hand side here, we have our elliptical galaxies, and then on the right side, we have our spiral galaxies. And visually, you can see a color difference. Hopefully it's coming up on the projector. You can see that the elliptical galaxies are more red, and that the spiral galaxies are more blue. So there should be 2 different galaxy populations because there are 2 different kinds of galaxies. So visually, we also expect that there should be a difference in photometric color using filters. Oops. So let's talk about each population separately. So on the top here, we have an example of elliptical galaxy. Elliptical galaxies are visually more red, as you can see, and that's because the star population in it is older stars, which are redder. And there's also very little gas and very little star formation because of the little gas. And that's called the red sequence. And next we have the green valley galaxies, which are transition or also called lenticular galaxies. And these are galaxies that are being quenched of their star formation via processes that we really don't know, most likely galaxy mergers, but that's like up for debate right now of why galaxies are being quenched in their star formation, which I won't go into today. But they're part of the green valley. And then lastly, we have blue cloud galaxies, which are young blue spiral galaxies that we see. The Milky Way is one of them. We know that we have star formation. And they're visually bluer because that they have a lot of star formation. Young stars produce a lot more bluer light than old stars. So now, why do we even care about knowing the different types of galaxies? That sounds like very Astro 101 type things that you would learn in high school. So, like I said earlier, I mentioned that but via galaxy color, you can tell a lot about the stellar population inside of those different galaxies. So here we have a color magnitude diagram of what's called the Great Wall, which is a galaxy supercluster in the coma cluster, supercluster area. The red galaxies up on the top, the red dots up here are all the elliptical galaxies, and the blue dots down here are all the spiral galaxies, and then the green dots, which are kind of everywhere, are all of the lenticular galaxies that I talked about. And making color magnitude diagrams are typical in working with clusters because it's a proxy for knowing the star formation rate of the different kinds of galaxies. And that's important for people who do galaxy evolution and research galaxy evolution. So, remember my question was can I do this with a random sample of galaxies? So, where do I find a random sample of galaxies is this Lone Digital Sky Survey. I used their latest data release, DR13, because that latest release, they have all the previous ones in it, so that one has the most galaxies that I could use. So they have all the photometric data I need to make color magnitude diagrams like this. So a little bit more about my data, because galaxy photometry is a little bit different than star photometry, because galaxies are extended objects. So you have to know the surface brightness profile of the galaxy. You can't just take an aperture and do photometry on it, because it's an extended object and there's gas in it and everything. So what Sloan does specifically, I looked a lot into how they reduce their photometric data for galaxies. They use a de Vaucouleurs profile and an exponential model to fit the surface brightnesses of the galaxy, and then they take the best fit flux and average both of those together, and then that's the magnitude that they pick via the best flux. And then they also use equal aperture photometry, both when they take the pictures and both when they reduce the photometric data that they have. So then my method, which was, I thought this was going to be a lot more straightforward than it was. I used a sample of 400 galaxies. That's just a totally random number. I figured that I would get enough of a sample out of hundreds of them. And I used IDL to calculate the color excess and make a galaxy color magnitude diagram. And I used 4 of the SDSS filters on their camera. They actually have 5. There's also a 5th one, but I didn't use that one. I don't know why, just random that I picked these. And SDSS filters, as you can see, these are not the typical Johnson UViz magnitudes or filters that we learned about in class. These are a little bit different, but it really shouldn't matter. I should get the same kind of distribution no matter what magnitude system that I use. And then finally, from these color magnitude plots, I will look at a histogram of distribution, because if there's a bimodal relationship, there should be 2 visible peaks in that distribution. So my data is really scary because the errors are large. This is the worst one that I made. So plotted on the y-axis here on all 3 of my graphs that I made, it goes from -6 to +6, and then the x-axis varies a little bit, but they were all about the same magnitude range that I used. So we have color on the y-axis and then absolute magnitude of the second color, so G for this one, on the x-axis. And as you can see, there is some that have small error, like these ones here have pretty small error, but then there's some, like this one doesn't even have a point on it because it was like way down here, and the error bars were huge, so I was just like, let's just pretend that one isn't there because it's ugly. And then we have, the next one is G minus R. Kind of looks nicer, there's less of an error. So we have G minus R color with the same y-axis, and then 24 to 34 instead of 22 to 32, absolute magnitude of R band. And then the last one is R minus I plotted on the y-axis again, from -6 to +6, and absolute magnitude of the I band again. So this one was kind of a little bit different because this one kind of has a trend that goes up like this and then down like this, which I thought was really weird because the other ones didn't have that. So even though there's large error bars, I felt like I still should have saw an overdensity in 2 spots if I did have a bimodal distribution. But remember that I want to look at the histogram of the distributions, not these ugly plots. So that's what I did for my 3 colors that I did. So here's my UG color bin, which was the first graph that we saw. So if you look really hard, you can kind of see a peak here, and then it drops down, and another peak, I don't know, but then this might be another peak, this might be another peak, I don't really know. So I said no to this one, that I didn't have 2 peak distributions. Because looking at other distributions like this, there were definitely 2 peaks. So I knew I was kind of doing it right. So, I don't know. Same with G minus R. This one's a little bit different because I have this one right here, which is strange. I don't really know if that's my other peak that I needed, but also this one kind of goes up right here too. So again, I couldn't say definitively that this one had 2 peaks. Same thing with my last one, R minus I. This one was the most promising because this peak was significantly higher, but also this one was way higher here. So I'm not really sure. I didn't like any of my graphs that I made, so I wanted to look into more of the literature about this subject and see if people did this with random samples of galaxies. And I found 2 distinct answers for what the answer to this question is. And I want to talk a little bit about what I found on that. Oh. So no, definitively, I don't have a bimodal distribution. At least to my confidence, I don't think I do. So the first paper that I found talking about this was Strateva, I'm not trying to say the name, from 2001, and they did almost the exact same study that I did, except they used a huge amount of galaxies. Now remember, I only used 400. And they also made a color G minus R plot and U minus G from Sloan. They used the same Sloan data that I did. Well, not the same, but they still use the Sloan database. But you can see on here that there's this distribution here and this distribution here. And they do plot the contours, so they're like pretty sure that these are over densities. And they said that they found a bimodal relationship. And I made color plots because I took their advice and was like, hey, maybe I should make the same graph that they did since I used the same database. And mine just looked like a blob and it was horrible, and I didn't want to include it. My other ones look nicer. So the next paper I want to talk about, I don't necessarily agree with their results. However, they did get the same answer that I said was, no, there's not a bimodal distribution, which is why I still wanted to talk about it. So Eels et al. 16, and hopefully you guys remember this plot because we talked about it in Journal Club. So what's plotted here is the specific star formation rate of a bunch of Herschel galaxies, which specific star formation rate is the star formation rate divided by stellar mass of a galaxy, which is kind of like color because, like I said in the beginning, the older the stellar population and the less star formation, it's redder, and then the more gas and the more star formation, it's bluer. So you can kind of imagine that like color, and then on the bottom here we have stellar mass, which is kind of like luminosity, which is kind of like magnitude. So this is kind of a weird color magnitude plot. And they say that the red sequence is just, should be, they said in this caption, they have second order polynomial, that this is the best fit line, but then later they made an actual color magnitude diagram and said that the relationship should be linear. So I don't really know what the difference between that is. But anyway, the reason that I wanted to mention it is because they said that there shouldn't be a bimodal distribution and that the red sequence is just galaxies falling below a certain star formation rate, which that's why there should be a red sequence. However, I still wanted to include it because they said no bimodal distribution. And that's the results that I got, which is why I wanted to talk about it. So now, knowing that there's two opinions on this subject, I wanted to look closer into my data. So remember what I said in the beginning of the talk, that I wanted to answer two questions if my answer was no. So I'm going to look at my data closer and see if there's a bias towards or against redshift, because redshift makes everything look redder, at least photometrically. Or against redshift, meaning I'm using too close of a redshift and there's not enough elliptical galaxies in my sample. And then also, is using a random sample a bad strategy? Because like I said in the beginning again, this is usually graphed with clusters, not with a random sample. So first, is there a bias towards redshift? So the SDSS median redshift, that how deep it can look into space, is about 0.1. So I used the SQL search because in order to search, you can't use the GUI that they have on their website. So you actually have to search for it using the SQL. I don't remember what that stands for. But I specifically looked for redshift, and then I also had it give me what class of object in the database that it needs. So there's 3 classes in the SDSS database: QSOs, stars, and galaxies. And remember, I specifically looked for extended objects like galaxies. So the high redshift things that it was outputting was QSOs, which I wasn't using. So I know that I don't have a bias towards redshift. And then my highest galaxy redshifts that I was getting in my random data generations that I did, the redshift was about 0.8. So that's not far away enough to be really redshifted, because I wasn't looking at spectra, I was looking at visible colors. So I said that maybe there might not be enough elliptical galaxies, because typically they're farther away, but it really, I don't think that that should have played a big role, but I guess it is something that I have to consider. And then next is my random sample a bad idea? And since these authors here in 2001 did almost the same exact thing that I did, except with a whole bunch more galaxies, I assumed that my data was wrong only because, well, not wrong, but I didn't have enough of a data sample to have a definite conclusion. And also, I did not use magnitude limited sample. They had everything that was about 21 and higher, apparent magnitude, and I just said, give me everything that you have, because I didn't know any better. I was just trying to make a galaxy distribution. And they also used data from one specific SDSS run on one night from March 22nd, 1999. And that was in this declination RA range, so it was only in one portion of the sky. So I didn't restrict my RA index, so I don't know if I'm getting like a lot of galaxies in the galactic plane, but really there shouldn't be, because that's not where galaxies are. But I don't know if there's a discrepancy there, but that also brings up another maybe bad thing about my data, is that I'm not considering dust obscuration, both from our galaxy and the galaxies that I'm getting photometric data of, because the more dust makes stuff redder. We know that from this class. And if there's a lot of star formation in a galaxy, that makes things look redder, even though the stars are younger and bluer. So I don't know if the model magnitudes that I used are dust corrected, but they're probably not, because I didn't really think about that until after I did this. So I don't know if that played a role, and I would like to look at that more. So I said that maybe using a random sample is a bad strategy because I didn't have a magnitude limit and I did not use a specific survey. I just said, from the database, give me everything, give me a bunch of galaxies that have these magnitudes. I didn't restrict anything like that. So in conclusion, no, I didn't find a bimodal color distribution. So I put a few things on how to improve based on the research that I looked into more, is that just use a bigger sample, because that probably, I mean, more galaxies makes everything better and more accurate. And also, it was recommended to me to use statistical methods like fitting a Gaussian to my distributions. I just didn't have time to do that. But that is something that I could do in the future to make my data better as well, and see if there's actually 2 peaks in there instead of 1. And then also, other studies have concluded similar results to mine, like the paper that I talked about, where that the red sequence shouldn't be 2 overdensities, because it's just a continuation of the blue cloud, and there shouldn't be 2 densities because it's like still connected. So then I also talked about how I could look into the dust obscuration more as well, how to improve. So that's all.
Okay, great. Time for questions.
Yes. And first.
Okay, why did you initially choose a sample size of 400? Why that number?
Literally because I typed 400 into the search. There was no rhyme or reason to that. I just thought that I figured I needed at least hundreds, if not thousands, and I didn't know how much IDL wanted to process in my computer. So
Okay,
I just made 400. Yes.
Could you go back to the slide that has the graph of the people that did find the bimodal distribution?
Yeah.
Farther back.
Oh, like the first one? This is the only one, the other one.
Okay, maybe it was that one then.
Okay.
Yeah. I was wondering if maybe what they did to analyze it kind of changed how they're, because what you did was just a straight up plot of things, color magnitude, but they said they did something called the Bayesian cut of the projection of the color space.
The Bayesian cut, like this dashed line right here,
Yeah.
this is where the theoretical line of where they think the separation between the 2 galaxy populations is.
Okay.
And the Bayesian separator is another, I think, actually, let me say that again. I think this is what they found from their data that should be the experimental line, and the Bayesian separator is the theoretical line.
Oh, okay.
And I think they were trying to compare those things.
Okay.
So I don't know if that makes a difference. I didn't really look into that, but I think this is a theoretical and experimental line of this should be where these cut off and ours should be separate.
Yeah. Okay. The only other question I had was, in your histogram, did you ever try like changing the bin width on it to see if
I did. I didn't talk about that, I'm sorry.
No, it's fine.
So I'll just use this one as an example. The smaller that I made my bins, this is a 0.2 bin because I took a 0.2 width across here and told my code, count how many galaxies are in this slice across across the graph, which came out as these. And the smaller that I made my bins, the more jagged and ugly it looked. And then the bigger I made my bins, the smoother it looked. So it didn't really give me more peaks, it just made it look uglier or smoother. And it wasn't giving me the result that I picked. So this, the 0.2 bin size would look the nicest, which is why I picked that. Yes.
So on the slide Victoria told you to go to the bimodal distribution, would it
Yes.
think that? I'm having trouble phrasing the question, but it doesn't look like there's 2 separate distributions there. It looks like they cut it in half and then did change what the symbols were and then drew contours for each one of the symbols.
So these,
how do they know they're 2 distributions then?
the contours are their like density distributions that they did, except they use like, instead of like density contours, like the first one that I showed at the beginning with the red, blue, and green colors, those had actual density contours, But these contours are like the probability that these are part of the overdensity, I guess.
Okay.
I don't know if that makes sense. But they also started with knowing which ones were elliptical and spiral, and I didn't. I wanted to see if I could pick that out from my data. So again, that is a little bit different.
Is that the difference between the dots then? They know the.
Yeah, these, I don't know if it's up there. The squares and triangles represent two main classes meaning spiral and elliptical. Yeah.
So if you know beforehand, then
That
it's like,
makes it really easy.
right, because it's one distribution if you just look at that,
Mm.
right? Yeah. So, any other questions? Well, we don't have much time, so I guess I won't be able to ask any questions. No, I'm just kidding. No, go back to
Hopefully I can answer that.
slide 6. And why do you think that there are few, or in some cases not any, dots outside of this shape? Like over here, it seems like a bunch are missing. There's nothing down here. There's nothing up there.
Like, why do they fall where they do?
Why are there no dots over here? Over here?
I guess theoretically they should.
If you don't know, that's okay too.
I guess theoretically they should be there, but I honestly don't know.
Well, how do you know
because-
theoretically they should be there?
Well, because I mean, galaxies can really, like, I guess that's like on a HR diagram, stars can technically be anywhere on it.
Not really, right? That they're in the main sequence and a few other places.
But I mean, I guess this is like the galaxy main sequence. That's a bad term that people don't like to use, but this is like how they fall in, especially because this is a cluster. So this is like naturally where they would fall.
What's this?
That's absolute magnitude in I.
So how did they determine absolute magnitude?
These people also use SDSS, and I'm not sure how they did absolute magnitude, but like how I did it was in the SDSS SQL query. They have a formula when looking for absolute magnitude that you plug into the query that it outputs absolute
But
magnitude.
the observation is apparent magnitude.
Yes.
And so you can only know absolute if you have a volumetric correction, which requires a lot of work actually.
I thought that this was the volumetric correction. I actually don't know what the H73 is.
Right, okay, so you have to know more about it. Is it the case, do you think, I think I know the answer to this, I'm not sure. Is it the case that one direction along this axis is brighter and one's fainter?
Yes.
Which one's fainter?
Over this side.
This side?
Yeah.
So is it possible that there's
Less
this edge
negative.
here because things are too faint?
That could be, yes.
Because usually when you see a color magnitude diagram or color magnitude diagram, which this kind of is, there's a place where you don't detect objects, not because they're not there, but you're not sensitive.
Yes.
And could it be the case that galaxies aren't this bright? Like maybe there aren't galaxies this bright. It's
I
part of
mean-
the luminosity function.
Yes, especially since this is a cluster. So,
Okay, right, which one is this, coma?
yeah, the coma supercluster.
Okay, so let's go to slide 10. Okay, we'll pass that. I'll go to 18. I had a question, it became less relevant. So this is one of those.
This is a rough graph, I know.
This is one of those cases where whoever made the plot knew the types of the galaxies.
I
Right.
think so, yes, because I think the colors
I
are
think
how
that's
they
what that
did
is,
it.
right?
Yes.
Yeah, okay. So if you just want to grossly talk about two types of galaxies, elliptical or spirals, then you might focus just on the dots that are red or blue here, right?
Mm-hmm.
Now, it looks to me that the red dots and the blue dots are in different places.
Yes. I agree.
That's the point. I don't think this paper's been published
Yeah,
yet.
that's why we fought about this paper in journal.
Yeah.
Because we
This
talked
paper's-
about this paper in Journal Club, and that's also what we said.
Okay,
And
so
then-
were you trying to present this to prove that there is a bimodal distribution or there's not?
No, I
Or neither?
presented this paper because they concluded the same thing that I concluded, that there was not a bimodal distribution.
Okay, so if you look here, it kind of looks like there is, right?
Yes, but this is the graph that they argued that there wasn't.
Okay, well, but it could be because they included intermediate cases here, right?
Yes,
Which tends
I agree.
to smear the distribution.
yes.
And I guess you don't know a priori what type of galaxy you're looking at, then you can't, it doesn't look like bimodal, that's the problem. It only looks bimodal after you know the answer.
Which is why I was trying to do it where, to see if there was a distribution, and then I would ask my question, like, see if I could
Yeah,
tell which ones
okay.
were.
The statistics you were talking about before is Bayesian, that's the way people
Oh,
normally
okay.
pronounce it. And it's a special kind of statistic where you take account of what's already known,
Mhm.
and you keep updating the probability,
Okay.
okay? There's a lot to it. There are people who only do Bayesian statistics as their whole lives. So I just summarized it in a few sentences.
Sure.
That's excellent. Okay, let's thank Meaghan again.